Hi children, good morning. In this video, we are discussing reversible reaction and chemical equilibrium. Reversible reactions and chemical equilibrium, part 1. Some chemical equations are given here. Burning of carbon. Carbon burns in air to form carbon dioxide. The reactants are carbon and oxygen, and the product formed is carbon dioxide. Can you convert this carbon dioxide back to carbon and oxygen? No, it is not possible. Let's consider the second reaction. Zinc reacts with dilute hydrochloric acid, and the products formed are zinc chloride and hydrogen gas. Here, can you convert the zinc chloride and hydrogen gas into the reactants back? Zinc metal? No, it is not possible. The products are formed there. You can't convert the product into reactant. And let us consider the third reaction. Here, an alkali, sodium hydroxide, reacts with the hydrochloric acid to form salt solution. It's a neutralization solution. The product is salt solution. Can you convert that salt solution into acid and alkali back? No, it is not possible. This type of reactions, that is reactants converted into products, are called irreversible reactions. That is, in an irreversible reaction, it is the chemical reaction in which reactants give products, but the products do not give back the reactants are called irreversible reactions. So, the above reactions are irreversible reactions. Reactants are converted into products, products never coming back to reactants. Now, let us consider an experiment. So, take a long glass rod, then take a piece of cotton and dip that cotton in ammonia solution and keep at one end of the this glass tube. Take another piece of cotton and dip it in hydrochloric acid and place that cotton at the other end of the glass tube. And both end of this glass tubes is covered with a cork, rubber cork. Okay. Then observe after some time. So, what changes happens in the glass tube? See that in the glass tube, you can see thick white fumes are formed inside the glass tube, and the thick white fumes are the formation of ammonium chloride. So, ammonium chloride is formed, and this is due to the reaction between ammonia gas and hydrogen chloride gas. They combine together to form ammonium chloride. So, after that, heat that ammonium chloride using a burner, heat that white fumes. That is, we are heating this white fumes of ammonium chloride. Let us see what happens on heating this ammonium chloride. On heating this ammonium chloride, see that white fumes disappear. So, what happened? That is, on heating ammonium chloride, it decomposes back to ammonia and HCl. And the reaction, that reaction can be expressed as ammonium chloride decomposes to form ammonia and HCl. See, in the first reaction, that is, ammonia is combining with the HCl to form ammonium chloride. Here the reactants are ammonia and HCl, and the product formed is ammonium chloride. But in the second reaction, that is, on heating this ammonium chloride, let us see what happened on heating this ammonium chloride. And the reaction can be expressed as NH4Cl gives NH3 plus HCl. Now, here ammonium chloride is the reactant, and ammonia and HCl are the products formed here. Thus, in this experiment, at first ammonia combines with the HCl to form ammonium chloride due to the forward reaction, isn't it? And ammonium chloride decomposes back to ammonia and HCl. These type of reactions are called reversible reactions. So, let us see what is a reversible reaction. A reversible reaction means the chemical reaction in which reactants convert into products and the products change back to reactants is called a reversible reaction. That is, the reaction takes place in both directions. Isn't it? And the reactants changing into products is called forward reaction, and the products changing back to reactants is called backward reaction. That is, in a reversible reaction, both forward and backward reactions take place. Now, let us see what are the features of a reversible reaction. What is the special characteristic of a reversible reaction? For that, I am considering another reversible reaction, formation of ammonia. Ammonia is formed by the reaction between nitrogen and hydrogen, and it is a reversible reaction. A reversible reaction we can express by a double arrow mark. So, at first nitrogen combines the hydrogen to form ammonia, and that is called forward reaction. And ammonia decomposes back to nitrogen and hydrogen, that is called backward reaction. At the beginning, only the reactant molecules are there. So, nitrogen combines the hydrogen to form ammonia by forward reaction. At first, the rate of forward reaction is maximum. That is, at the beginning, the rate of forward reaction is maximum. As the reactants consume, the rate of forward reaction slowly decreases. As a result of this forward reaction, ammonia is produced. When ammonia is produced, backward reaction starts. At first, that is the backward reaction, the rate of backward reaction is very slow. As the quantity of ammonia increases, the speed of backward reaction increases. That is, as the reaction progresses, the rate of forward reaction decreases and the rate of backward reaction increases. Finally, their speed became equal. The rate of the forward reaction will be equal to the rate of the backward reaction. This state of a reversible reaction is known as chemical equilibrium. That is, a chemical equilibrium means chemical equilibrium is the stage at which the rate of forward reaction becomes equal to the rate of backward reaction. So, all reversible reactions are attaining chemical equilibrium after some time. In an equilibrium, the rate of forward reaction will be equal to the rate of backward reaction. All reversible reactions are attaining chemical equilibrium. Then let us see what are the special features of a chemical equilibrium. What are the special features of a chemical equilibrium? See, and at equilibrium, both the reactants and products coexist. In a reversible reaction, forward reaction is taking place. At the same time, backward is also there. So, reactants and products are present in an equilibrium. And we already discussed the speed of the forward reaction and backward reactions are equal at equilibrium state. Once equilibrium has been attained, there will be no change in the concentration of products or reactants. That is, when the equilibrium is reached, the concentration of the reactants are not changing because the speed is equal. Forward and backward reactions taking place at equal speed. So, the concentration of the reactants or products are not changing. And equilibrium is dynamic at molecular level. Molecular level, it is dynamic in nature. So, a chemical equilibrium we can call a dynamic equilibrium. At molecular level, it is moving. Dynamic means moving, not static. Equilibrium is possible only in a closed system. What is meant by closed system? It is the one in which nothing is new is added in it or nothing is taken from there. In a system, we are not adding anything to the system or we are not removing anything from that system. That is called a closed system. So, an equilibrium will continue only in a closed system. So, these are the special features of a chemical equilibrium. Now, let us see that is how to represent a reversible reaction in a graph. That is graphical representation of a reversible reaction, graphical representation. See, let us see how to represent. And we have y-axis as well as x-axis. And on x-axis, let us take the time of the reaction, and on y-axis, it is the speed of the reaction, rate of the reaction. And when we consider a reversible reaction, the first reaction is forward reaction. reactants are converting into products. And the speed of the forward reaction is maximum at the beginning because all the reactants are there. So it is maximum at the beginning. So a forward reaction, it is starting from a maximum point. The speed is maximum. As the time consumed, the speed of forward reaction slowly decreases because reactants are consuming. So the speed is slowly decreases. So the graph B, it represents the forward reaction. From maximum, it is decreasing. And when the product is formed, the backward reaction starts. So at the beginning, the rate of backward reaction is minimum. At first it is 0 and it is minimum. As the product increases, the quantity of product increases, that is the speed of the backward reaction slowly increases. So from minimum, the backward reaction, speed of backward reaction, it is slowly increasing. So the graph A represents a backward reaction. So graph B is forward reaction and graph A is backward reaction. Finally, what happened? Their speed became equal, that is they reach chemical equilibrium. So the point C represents chemical equilibrium. At C, the speed of forward reaction and backward reaction became equal. So once this equilibrium is reached, the system is continuing that is equilibrium. If we are not disturbing that equilibrium, it will continue. So this is the graphical representation of a reversible reaction. Forward reaction, backward reaction, and the coinciding point, chemical equilibrium. So that is the end of part 1, chemical equilibrium, and the part 2 will be presented in the next video. Thank you.